Yes, today we are really going to tackle a very simple physics coding challenge. And then we are just going to test our knowledge in scientific computing. And everything that we are going to do, we are just going to use C++ programming language. So we have this question here. We went to the lab to perform some experiments to actually verify Hooke's law. And then from Hooke's law, we know that the force is directly proportional to the extension, right? So this using the from the experiment that we performed, we are supposed to use the data point to actually predict the extension that will be provided by 0.5 kilogram mass, right? And then after we are done with this, we are supposed to save the result of our computation. So the sample data we have here is we have the mass and then we have the extension. And from this data, we are supposed to be able to predict our spring constant, which is actually the slope, right? So if you don't really understand Hooke's law, I'll try as much as possible to give you the theory behind Hooke's law. But the at the end of the day, we are supposed to get something like this. This is the code I wrote. I'm going to comment all of these out and rewrite the code for you to understand. And this is spring data. Okay, these are data file. This is the file that we read from, and then this is the executable file that we were able to produce, okay, by compiling the source code here. So we decide to if we decide to run this program, okay, let me run this program so that you have a feel of how the program is. Okay, so if I run this program, that's my let me run this executable. If I run this program, it's just going to basically read from the file and tell me the mass, the extension, and then the force, okay, of each mass. And afterwards, the program calculates the slope, which is basically the extension 39.998, and then the intercept, okay. And then based on those values, it actually predicts the extension of a 0.5 kilogram mass. That's very, very simple. So let me comment, this is what we expect. So at the end of the day, these results are supposed to be output into a result file, an output file. Okay, the output file, and this output file. So anyone who sees this output file will have a general idea about the information that the data point provides us. That is the point. Okay, so let me take you through the theory behind the physics. Okay, so from Hooke's law, Hooke said that the force is directly proportional to the extension. So the greater the force applied on a spring, right, the greater the extension of the spring. And that is provided the spring does not exceed its elastic limit. So this can be produced into an equation. So the F is equal to K, right? So this K is actually a constant called the spring constant, and it indicates the stiffness of the spring. Perfect. So this equation, a plot of the force against E is actually going to give us a straight line passing through the origin. That's what we really expect from theory, F over E. So we get a graph that looks like this, okay? And this is actually the slope. So, but for real world examples, we are not going to get a perfect straight line or a line of best fit in which all the data points are on. Okay, we are going to get some that are either under or that are like above or below the line of best fit. Okay, so what we do is that we know the equation of a straight line looks like this: y equals bx plus a, right, where the b is actually the slope and then the a is actually the intercept. Okay, in our case, the b here represent the 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 spring constant, and y here represents the force. Okay, that's the force, and then the x here represents our extension. So that's perfect. Now, how do you get our B and our A? Okay, we need our B and our A so that we can predict any X or any Y. Okay, giving X, we can predict Y. Giving Y, we can predict X. That's what we need. Okay, so to do this, we use least square method, right? Least square method. I'm not going to go through the details of it, but I'm just going to write out the formulas to calculate the b and then a. So we know b is actually equal to n sigma xy, product of xy, minus sigma x sigma y all over n sigma x squared minus sigma x all squared. And then to get my a, I need a is equal to sigma y minus b sigma x all over n. So now let's take note of the variables that we will actually need to compute b and then a. So to compute b, I need the summation of the product of xy, meaning the first and then extension. I need summation of x, meaning the summation of all the extension values, summation of y, and summation of x squared, the extension squared. Right? These are the variables I need, and I can actually get that. Okay, so this is the whole theory that we are supposed to understand before we can write a code. Okay, this is what we need. Now, if you go through the code, okay, basically let's start from scratch. Okay, let me start. So if you are supposed to start, you just have to create a folder. Okay, a folder. Let me close this. You have to create a folder on your desktop or anywhere that you can actually locate it, and then give it a nice name. I gave mine spring constant. Now I open this folder, and I would like to open this folder with Visual Studio Code. If you have any favorite edit test ID that you have been using, you can go ahead and use. You just have to know how to go about things. So I want to open with Visual Studio Code. Very simple. So with this Visual Studio Code, since I'm supposed to write a C++ code, I need a file, right? A C++ file. So this is my C++ file, and these are the piece of code that I have. Okay. Now let me comment this code out. I would like to comment, select all, and then I'll comment it out. So if I comment this piece of code, is basically going to mean that they will not compile, or they are not really going to affect. They are not going to really. They just give information to a different programmer who intends to really understand our code. So let's comment this out, and then we take each one at a time, right? So this is what we do, right? Now what we are going to do is that, let me try and collapse this. Okay. So first of all, we need to import some header files, and header files are simply pieces of code written by someone else, right? Okay. We need to get the header files. Okay. The ifstream header file, and then since we are going to read from a file and then output to a file, we need a ifstream header file as well. Then I'll need some few functions from the std, right? The namespace std. So I'll need cout, I'll need sendline, and I'll need input file stream and then output file stream. Okay, perfect. This is what I'm going to need, and probably I'll need int main. Okay, so I'll need int main. Okay, so now my int main is just the entry point. Okay, so int main, and int main is supposed to return 0 if everything goes on well. So my first goal is to be able to read the content of spring data.txt. That's my first goal. Okay, and it should be simple. So first of all, I have to have a string. So I have to first of all have a string that has that stores the name of my data file, right? And then with this computation I'm going to use 9.81 as the acceleration due to gravity. Okay, and then I would want to create an instance of my input file stream. Okay, and then this instance of an input file stream takes in the name of my input file. Okay, and in this case, just the name spring data.txt, and I want to read it. Now, before reading from this file, I have to first of all do a check. Okay, I have to do a check to see if my input file is open or not. If my input file is open, then it means the file can be found in my directory. If I can't find it, then it probably means that it doesn't exist on it. So you should just return an error message and then return one, meaning it didn't go as planned. Okay, so at this point, let me just save and then compile. You see, if I don't get that error message, it means everything is fine. If I get that error message, it means it can really find my file. Okay, let me clear it. If you compile, you just need this, right? So this is actually the compiler that will compile your code. It takes in the source code that is supposed to compile, and it has an argument which allows you to give it the name of the resulting executable file, right? In this case, Spring. So if I do that, everything went on well. So um, this Spring thing is generated for me. I can actually run this to Spring. Nothing happened because this didn't happen as well. That's it. So now let's move on to the code. Now if now we can find if we can find the file, then this is what we want to do. Wow. Okay. Wow. While is not the end of the file. So we are saying that since you can actually locate the file, right? Since you can actually locate the file, and it's not really the end of the file. Okay, you have not read to the end of the file. I need you to get the mask. I need you to get the extension for me. So to get this, I need to really create variables that will actually store the mask and then the extension, right? Perfect. And now I'll pass the line to extract the mask. Now I want to extract the mask. So when you look at my Spring Data here, if it get to this line, it will be able to read the mask and then the extension. That's basically the whole idea here. And then it uses the mass to calculate the force. Okay, that's what I. But you realize that there is this first line here. Okay, the mass and then the extension. I don't really want them to affect my calculation, so I need to find a way to read them off, right? So to do this, I just have to just create a string here and call it. I just want to read that first line off. Okay, so I want to get line and read that line off. So I think it's coming from std. Same to this. So std, and it should be fine now. Right, perfect. So at the end of the day, I'll have the first line being read off, and then the rest of the content of the file is just the values, the mass, and then the extension I will need. Okay, so that's what is happening here. So now, since I've made changes to my source code, I have to recompile again. Okay, so I'm done compiling. Let me run. Perfect. So now at the end of the day, if I run, I'm getting the mass, extension, and then the force. So my code is actually able to read my file. That's the first thing. Now I've been able to achieve my first goal. My second goal is to actually find a way to calculate the slope and then the intercept. Okay, and I will use that to predict the extension for a 0.5 kilogram mass. Perfect, right? So with this, let's come back to this, to B and then A. Now in this x, remember x becomes our extension, and then f, y becomes force. Extension, force, this extension squared, this is summation of the extension squared, and this is summation of the force, summation of the extension. That's what we have to know. So this is what we can do here. Let me just copy what I have here. Okay, let me just copy this. Okay, let me copy what I have here. and paste it here. Okay. So, and let me uncomment this time. Perfect. So now I have float some f, some of the false float, some of the extension, and so on and so forth. So this is what I have, okay, and this is what I have. Now in every iteration that I do here, I, okay. So in all the iterations I do, I want to keep on updating some fx, some f, some x, and so on and so forth. Okay, and that is pretty easy here. So this is what I really have to do. Okay, I just need to copy this. This is what I really have to do in doing my iteration. This is what I need. Alright. Okay. Perfect. So now anytime the iteration, the while loop runs, and I needed to keep track or update the fx, right? And then fx is simply false. So anytime it runs, it's calculate the product of the false and then the extension, and then it just add them to the previous sum. So at the end of the day, I'll get all the variables that I will need, and every iteration update the count. This count is actually keeping track of the data point that we would have, assuming we are supposed to actually plot them on a graph. Okay. Now let's do a check here, right? Now at the end of the day, we need to calculate the slope, okay? And then perfect. We need to calculate the slope, and then the slope is just given by this, and then the intercept is given by this. That is what we have, okay? That's how we have to do it. That's the understanding, okay? So we just have to put them in. So at the end, we would have the slope, and then we have the intercept. So that's perfect. So I think now let's print out the slope and then print out the intercept. So now we can print out the slope and then the intercept. Okay. So now so this is it. So now this is it, the slope and then the intercept. Perfect. So now I have to compile again. Those using if you are using Embarcadero or Dev C++, it's just a matter of clicking a button. So it's not really a big deal. So Spring. So now at the end of the day, now I have my slope and then I have my intercept. Okay, so I can just come back to theory and fit them. Okay, so from theory, since I have my b and a, I can modify this equation to be now false is equal to my b, which was given by, which is 39.998. So 39.998 e, right, which is the extension, plus my the intercept, okay, 0.0173588, 0.0173588. This was my intercept, okay, and it's actually a straight line, but it's just that it's not passing through the origin, and it's fine. So this is the model that I'm going to use. This is what will help me predict either the false, predict the extension given a false, or the extension, the false given an extension, right? But for the question I have here, the goal is to predict the extension for a 0.5 kilogram mass, right? So this is what we do. This is what I'm going to do. Okay, so it's very simple. So I'm just going to copy the code I have here, right? And I'll just explain it. Let me copy and paste it here, just to make things fast. Okay, I don't want to type all of these. Good. So now okay, So now I need my output file, right? Okay, first let me comment this out before I bring the issue of output file. So if I comment this out, right, now I have to create a variable that will hold the mass that I want to predict its extension. So floats force for prediction, right? The force for prediction is 0.5 kilogram, and then my G is given by 9.81, so it actually gives me a force. And then my predicted extension. Now from theory, we can make E the subject from this equation here. So to make E the subject, E is equal to my force minus 0.0173588 divided by 39.998. That's it. So this 0.0175 is basically my intercept, right? And that was the A. Okay, and this is actually the B. So it's just F minus A divided by B. As simple as that. So that is what we have here. Force prediction minus intercept divided by the slope. Okay, and then let me see, let's run this code, and then this line is just printing out the predicted extension for us. Okay, so let me compile let me clear the terminal here, and then let me compile. So I'll compile again because I've made changes, and then spring. So very good. So now I have my slope, I have my intercept. Now predicting extension for a 0.5 kilogram mass. So now the extension for a 0.5 kilogram mass is 0.12297 meters, and it makes sense because if you look at the data point I have here, a 0.05 mass is given has an extension of 0.012. Now when we check the 0.4, it's giving 0.098, meaning as the mass progresses, we are going to get a greater extension. And this 0.5 kilogram mass is expected to have a greater extension more than the 0.4 kilogram mass. So for our result is actually making sense. Okay. So now since we have this result, we would like to save the result in data file. But before that, let me delete this. Okay. Let me delete this output file. Let me delete this. Okay, let me just move this to trash. Now if I delete this, I want to be sure that the program is working. So this output file to all right, let me go here, and then I also have to create a variable that will store my output file. Okay, so I need to also create an instance of the output file. Okay, and this instance of the output file takes in the name of the output file. All that we see here, we can actually make it dynamic, okay, so that it's not like it's being hard coded here. And anytime we work with files, we have to close it. Okay, we have to close the file. Now let me uncomment this. So I want to output the slope, the intercept, and then the predicted extension. Instead of slope, okay, it's KB, and then the intercept B is fine. And then the predicted extension. So at the end of the day, I'm expecting a file which has the slope, the intercept, and then the predicted extension for a 0.5 kilogram mass. So just save, and let me compile again. And then we compile. So now do we see this? Now we have a very the same result, but this time we have an output file, and that is what we want to achieve. Now let me make things a bit difficult. Now I'm giving you a challenge. Now the challenge is, instead of we hard coding the name of the input file and then the output file, I want you guys to make it dynamic so that the user actually does that. Okay. And then the predicted value for the masses, I want you to also make it dynamic so that the user rather enters the value of the mass that it wants to predict the extension for. Okay, if you do that, just get in touch with me. Bye.